are not designed for those movement, then the failure of seals happen, which causes leakages and draft. The displaced mullion caps. So this is very common sight. Whenever you see a capped curtain wall, you see cap of the curtain wall falling off or getting disengaged. That is again because of the fact that when we hand over the structure or hand over the facade to the occupant or to the customer, we try to do it to the highest possible workmanship level, which actually means having all joint hairline, which is actually not correct in most of the cases, but that's how we do it. And as soon as the expansion happens in those components, this component starts getting disengaged. So this will touch up in the following slides also. Now, when we understood what caused the movement, what are the impact of building movement on the building facade, we should also understand what should be looked at. Actually, there are many factors we should look at. 3 factors which should be looked at the very first stage at the scheme design itself is, first is the gravity loads. So what is gravity load? The loading created by gravitational force of Earth is gravity load. Since this is always present, we can estimate it very accurately and with quite a precision. So what forms part of gravity load is a dead load of host structure. So the self weight of structure itself and the gravitational force make the gravity load. And most of the time, almost all of the time, the movement due to this gravity load must have already occurred before the facade is installed, because by the time you start installing facade, all the props must have been already removed, and whatever deformation was supposed to happen due to dead load, that must have already happened. Next is the dead load of curtain wall itself. So as you start installing curtain wall on the building that starts loading the building with its own weight. So we see a typical pattern, like say a single floor has say 100 panels or 200 panels, and we start installing panel from one side, and by the time we are installing 100th panel, we realize that the first, second, third panels were out of alignment now. Why? Because when we were loading the panel sequentially, we were actually deflecting the building more, and then we have to again do the alignment of all the panels. This is very common practice in unitized facade. So unitized facade, that is how it is done. So we install all the panel together and then level it off, then start the second layer. Third part of the gravity load is imposed load. These can be semi-permanent in nature. So the temporary partition wall forms a part of say imposed load, and this kind of movement may or may not have occurred. When I say may or may not, so there are instances when the flooring happens after the facade is installed. So this flooring is a part of imposed load. Now, what kind of flooring, what kind of loads, that will depend on what kind of movement. Live load. So live load are transient. This have to be accommodated by facade in all the cases. So we need to be very sure. We need to be very sure that what is the actual live load deflection and what needs to be accommodated there. There are other gravity loads which are column shortening, creep, settlement, and shrinkage. Now these 3 forces together can make up to 3 millimeters of deflection per floor. So if you have a 10-floor building, that means in say 30 years of lifespan, it may be shorter by 30 millimeters. Here's the example which is trying to explain the various load given here. So this sketch on the right shows 2 columns and a beam, or say a floor slab. Now, as soon as this is casted in place and props removed, the first thing which happens is the deformation due to dead load. That happens automatically. So as soon as the props are removed, scaffolds are removed. So if this first level of deflection happens within a month's time, and then the second is the imposed load. As we start doing say flooring and start putting equipments on it, those are the part of imposed load, and this may or may not have happened before installation of facade. So this particular deflection level must have been addressed by the facade design. Third, which is the most important one as far as the movement accommodation of facade is concerned, is the deflection due to wind load. This essentially has to happen after the facade is installed. Now, if you see all three together makes the allowable deflection. So that is the allowable deflection, which is stated in many of the tender specification. And how does this allowable specification comes is on the specification of say IS 456, which is the code for concrete, Indian Standard 456. It says allowable deflection for beam and slabs are L by 350. So if you convert to a 6 meter span, L by 350 is about 17 millimeter. Now most of the time our tender specification must be saying that the facade should accommodate the movement of L by 350, which turns out to be 17 millimeter in case of 6 meter span. And mind this is not easy task to accommodate 17 millimeter of movement in any of the facade design. But thing is, we generally do not face problem, and that is the reason it just goes as it is. So what happens is this should be broken up into three parts: what is happening due to dead load, what is happening due to imposed load, and what is happening due to live load, and then the proper system has to be chosen. Mostly these beams are generally designed for stresses, and most of the time structural engineer is actually not bothered to calculate the actual deflection. So beams are designed for stresses. So maybe your allowable deflection is 17 millimeter. Maybe as per the beam design, your calculated deflection itself should maybe 12 millimeter or 10 millimeter or maybe less than that. So this goes as of now just as it is, without realizing the consequences of this. But as we are going more lean, as we are going more taller, so this becomes a point of concern for us. Moving on to the next slide, the next part which we should definitely look at is the lateral load. So what is lateral load? So lateral load is essentially wind load and seismic load. So wind load is dependent on the three main factor: terrain, where it is located, what is the height of building, what is the category where the building is located, where the building is located in the densely populated area, or it is on the seaside, or in the top of cliff. So those all factors determine what is the applicable wind load of the building. Here what we need to note is there is only 2% probability of reaching the design wind load each year, and that 2% is actually statistically related with the 50 years design life. So next is the seismic load. Now some of the tender specifications specify that the facade should be designed to resist the seismic load. No facade can resist a seismic load. So seismic loads are very high. So none of the facade can actually resist seismic load. Then what a facade can do? Facade can accommodate the movement generated by seismic load in the facade system itself, if that is known. Now how this can be determined? This needs to be assessed by structural engineer of the building. If we ask say specialist facade fabricator to assess the building movement due to seismic load and issue a tender, then we are planning to fail. This is by any chance, no matter how expert the cladding designer is, he or she will not be able to assess the seismic load. So this essentially has to be assessed by seismic engineer, structural engineer, and cladding engineer designer has to make sure that all the movement which is created due to seismic load is addressed. Third part, impact load, accident load. Sometimes these can be very difficult to assess. So nobody will actually design a building which is to be hit by aeroplane. So sometimes this can be a big forces. Other time, the impact load may have very localized effect. We may or may not want to design for some impact load because the impacts are very localized. Probability is very less, and we may decide to rectify it as and when it happens. So the sketch on the right side shows a curtain wall assembly where, for the ease of understanding, I've just shown one panel. So the wind blows from the left side, and this causes the inter-story drift. Like I explained I mentioned in the earlier slide, the slab one slab over with respect to other slab starts moving. The movement can be 3, 4, 5, 15 millimeter. And due to this movement, if you see, the movement is accommodated by the rotation of the mullions. So mullion has rotated to particular angle. And due to this rotation, what happened is the edge clearance between the glass and the frame reduced, and sometimes it touched the frame if it is not properly designed, and that may cause the glass to fail. When I say fail, fogging of unit is also failure, breakage of unit is also failure. So this is one very common practice used in industry. This can using this technique, we can easily understand what is the kind of edge clearance required. The next technique which is used by industry is the movement accommodation by sliding of frame. So if you see here, the glass is not at all stressed. So glass is resting in its place, no additional stresses on glass. But what needs to be looked at the jamb. So left jamb and right jamb. So when you see left jamb, the left part of the curtain wall, the additional gaps are created, and right part of curtain wall, the frame is hitting the structure itself. So when somebody is designing a curtain wall facade which is accommodating movement by sliding, they need to be very much worry of the fact that what happens on the jamb. As this is very important when we are doing the corners. So we do a excellent unitized curtain wall which accommodates a lot of movement, but do a glass to glass joint without realizing that this has restricted a lot of movement within the facade itself, or movement without breakage. So this is the movement accommodation happening due to the sliding of frame. And next thing, if we go to, which is the temperature load. So first was gravity load, second was lateral load, and third, which is most important. So gravity load, like I mentioned, is where we can estimate fairly accurately. Lateral load, it is all statistical based approach. So there are always chances of errors. It can be higher, it can be lower. Temperature load. Now temperature load falls in between gravity load and wind load. Although we know what is the kind of change in temperature can happen, but this can also be a probability theory. So what causes temperature load is change in temperature. So what happens when the temperature change? So generally, when I say generally, because there are exceptions in this case also. So increase in temperature is equal to expansion. So whenever the temperature changes from say 30 to 60 degrees Celsius, whatever element is facing that is going to increase its size. And decrease in temperature is related to contraction of the building, contraction of the component. Generally, these movements are very easy to calculate. If you see the very easy equation, delta L is a change in length is equal to coefficient of thermal expansion, CT into the length of the member, and delta T. Delta is the change in temperature. So that you can easily estimate what should be the change in length. And similarly, you can also estimate what is the strain. So what is the CT into delta T becomes a strain. So this strain is responsible for the stress. And you can also estimate what is the stress caused inside the structure. So either you design a component to accommodate the movement or accommodate the stress. So one of the philosophy is generally followed. Most of the time, we generally design a system to accommodate the movement rather than increasing the stress in the system. Here, what matters most is the relative expansion and contraction of the element. So maybe some of the time, absolute expansion is not a problem because that is accommodated in one direction. But relative expansion, when we say relative expansion, what does it mean is, if you see the table on the right side, it says coefficient of thermal expansion, which is raised to the power 10 to the power minus 6 per degree Celsius. Just for the understanding, we'll say this is per unit. So if for the same change in temperature, aluminum expands by 24 units, glass expands by 9 to 11 units. So that differential expansion is to be taken care of. Okay. And similarly, if you see here, UPVC has the highest CTE, the 40 to 70. That means for the same change in temperature, UPVC will expand or contract by much higher margin, maybe 4 times than of glass. So on the table just below it, the block just below it. So for the sake of understanding the movement caused by thermal change. So for a temperature change of 40 degrees Celsius or 4.2 meter mullion, which is a standard generally used slab heights, 4.2 meter aluminum mullion will expand or contract by 4 millimeter. So if the temperature is increased by 40 degrees Celsius, so the mullion size will increase by 4 millimeter. Similarly, for the 3 meter glass edge, that is generally standard size, glass will contract or expand by 1 millimeter for a change of 40 degrees Celsius. 6 meter steel beam will change its size by 2.88 millimeter, and 3 meter UPVC profile. Mind this is only 3 meter UPVC profile can change its size by up to 8.4 millimeter. So that is the kind of relative movement can occur in the component itself. So we understood what we should look at as a loading part. Now, what are the types of movement this causes? Moving on to the next slide, we'll understand what are the types of movement. So one is change of size. So like I explained, change longitudinal 4.2 meter mullion becomes 4.204 millimeter mullion. So that is the longitudinal change in size. Second is change of shape. So as the slab deflects or the beam deflects, the panel hanging on the beam starts opening up from the bottom and closing up at the top. Second is inter-story drift, causes the shear, and we see the deformed shape on the right side. And fourth thing which happens is the change of position, that is rotation. So movement accommodation can happen due to sliding, due to rotation. So this is the change of these are the three major type of movement change types of movement. Now, in terms of scope, there are two areas which we need to look at. One is the building movement. This essentially has to be assessed by a structural engineer of the building, and cladding and movement related to cladding. This has to be designed by the cladding engineer. So they need to make sure that whatever material we are using, whatever coefficient of thermal expansion they have, we provide movement joint to accommodate those movement, or we design the component to accommodate those stresses. Now, moving on to the next slide. What are the strategies we can follow? This I try to summarize in few 4-5 slides. What are the strategies generally followed in industry to accommodate movement? One is to provide edge clearance. So what is edge clearance? Edge clearance is the space between the frame edge or face of the frame and edge of the glass. In the diagram on the right side, if you see A is the frame and B is the edge of the glass. So that is the edge clearance. If we have edge clearance, this edge clearance determines what is the movement can be accommodated here. So edge clearance is one primary factor which determines the movement accommodation capability of a system. Then on the then it says what is pane size, edge clearance, opening daylight size, edge cover, and rebate depth. Next, moving to the next slide. The next strategy to accommodate movement is provide movement joint. So this is one of the most popular technique we use for accommodating movement, providing movement joint. Now, most of the cases, whenever we provide movement joint, silicon is the widely used sealing material, and most of the silicon has a movement accommodation factor of 25% to 30%. So when we say movement accommodation factor of 50%, which actually means a 10 millimeter joint can expand to 15 millimeter, or can expand to 12.5 millimeter and shrink to 10.5 millimeter. So there are some sealant in the market which can accommodate expansion to the tune of 100%, expansion to the tune of 100%, and contraction to the tune of 50%. So contraction cannot be zero, because once the contraction factor is zero, the gap becomes zero, which is not possible. So in case we are not sure what silicon is going to be used, we need to estimate all our movement based on movement accommodation factor of 25%. Most of the sealant falls in this range. in movement joint, we also need to make sure that bond breakers to be used. Now, what these bond breakers does is this decide whether the sealant is going to adhere on 2 side or 3 side. So whenever you design a movement joint, you need to have a 2-sided adhesion, because when your sealant is adhering on all 3 sides, it stops all the movement and the silicon fails due to the shear forces developed within the movement joint. And whenever we are designing movement joint, we need to make sure we need to design the movement joint for total movement. When we say total movement not only because of thermal and building, but also due to tolerances. What is tolerances? So tolerances are, say, manufacturing tolerances, fabrication tolerances, and installation tolerances. So you may order a glass size of, say, 2100 by 1500, but what is the chances that you'll get exact 2100 millimeter size? There's 0% chances. So these tolerances also built into the movement design itself. In our industry, popular joint, butt joint is very popular joint type. This joint type is shown in the sketch on the below and on the right side also. Is used between 2 glazing and cladding panel. The primary function of this joint is butt joint is weather sealing and to accommodate movement. So weather seal, it restricts the water and air to pass through. Standard width to depth ratio is 2:1. Many a time 3:1 is also used. Max width, which we can go up to, is 40 millimeter with using special technique. We should not actually go about 30 millimeter, but 40 millimeter still can be achieved. But this may need a special recommendation and consultation with the sealant supplier. The next joint type, which is shown just below the sketch, is lap joint. So lap joint is used for structural bonding glass panel to frame. So whenever we see structural glazing, so the sealant which is used to bond frame, aluminum frame and glass is your structural sealant, and there we see a lap joint connection. And in this lap joint connection, if you see the sketch on the right side, the glue line and bite is shown. Glue line is responsible for movement accommodation. Bite is responsible for adhesion of glass to frame. So if you have high wind load, low wind load, weight of glass, that all determines the bite size. But what determines glue line is what is the kind of movement need to be accommodated. Now the primary function of this lap joint is bonding. So it is responsible for sticking both the things together, and again movement accommodation. So movement accommodation is common between both. For butt joint, primary one more function was weather seal, and for lap joint the additional function was the bonding of panels. So moving on to the next slide. This is very common strategy we follow to accommodate a movement in the facade. Like I mentioned, I showed one of the cases where the cover cap was getting disengaged. So cover splices are very common technique. Cover splices are very common technique. So you provide a splice joint where you provide sufficient allowance so that the thermal expansion and contraction can happen without restricting anything, and then you always are worry free and never disengagement, de-snapping of cover cap happens. Similarly, on the mullion side, the vertical splice plate is used. I've seen many of the places where people tend to screw on both the side, considering that this makes it more stronger, but that is a misunderstanding some of the people has. So this joint is specifically made to absorb the movement. So one of the mullions should be free to slide up and down. Correct use of bracket is another strategy. So there are 2 types of bracket which is used in curtain wall. Curtain wall is one is only for the one is only for the restricting wind load, and second is restricting wind load and dead load. So the bracket which is shown with 2 arrows on the bottom of the correct use of bracket, that is showing a bracket which can resist both wind load and dead load, and above 2 red arrows shows a bracket which can resist only wind load and will not resist anything against dead load, and the 2 arrows shows this is free to expand and contract in this direction. Next thing which is commonly used for the large glazed curtain wall, large glazed stick curtain wall. Split mullions are used at every 20 feet to 30 feet distance, so that the built up of expansion, in the last slide I mentioned the things we need to worried about is built up of tolerances, built up of expansion. So built up of expansion can be accommodated here. So split mullion is another technique which is used for accommodating movement. Moving on to the next slide, we see an elevation of a particular curtain wall assembly. Here the detail shown is of a stack joint. So in unitized curtain wall, stack joints are very efficient to absorb movement. So this stack joint can absorb movement in vertical direction and in left and right direction. So in plane, in both the direction. So if you see the animation on the right side, so it is just getting a little. I'm just getting a lag. So this stack joint, if you see on the right side, so this shows the top part is free to move. So this top part can move up and down and left and right. So on a standard basis, such stack joint absorbs movement to the level of 8 to 10 millimeter vertically and probably 40-50 millimeter horizontally. When you are accommodating 40-50 millimeter horizontally, you are actually looking at the connection at the jamb to ensure nothing wrong happens there. So that is a strategy to accommodate movement in a unitized curtain wall. This brings us to the fact that there are many areas which are not following integrated approach of design. Like what is recommended here is what we should do during the design stage itself. Architect has to do the following thing, like he has to decide what is the kind of supporting structure to use, what is the option for cladding system, what are the grid dimension, and based on this information, structural engineer need to understand what is the cladding system is used and what are the limits of those cladding system. So if you are designing a bespoke cladding system, then it is a different thing. But most of the times, designing a bespoke cladding system is very much cost demanding, time demanding. So at the initial stages, structural engineer need to understand what are the cladding system is going to be used and what are the limits of those, and then accordingly size the structure to limit the deflection of the building, to limit the movement and deflection of the building within that range. And at this instance, cladding detailer is responsible for providing all the inputs, what can be accommodated, what cannot be accommodated, what are the limits for stick system, unitized system, bespoke, unitized or panelized system. So next is the structural design part. During the structural design part, architect again provide information on the proposed cladding movement requirement of proposed cladding system, maximum weight of the cladding, position for transferring the cladding loads, and the structural engineer calculate actual structural movement and interstory drift and floor deflection. Here the point to be noted is the floor deflection which is being calculated here needs to be calculated in three parts: load, cladding load, and live load, which was explained in the earlier slide, that what happens when. And cladding detailer at this point of time is estimating the cladding movement and arrangement of transferring the load, movement accommodation of the cladding. And at the final stage of cladding detail, cladding detailer provides the information in one go, which is agreed by architect, and structural engineer confirms the acceptability of the calculated loads. So this is the brief recommendation. I use the following references while developing these slides, which is given in slide 16. And just to summarize, what we discussed today is on the slide 17. So we discussed from causes of building movement to what impact it does on the structure. So what impact it does to the structure, and then what is the kind of loading we should really look at very early stages, what strategies to be employed for movement accommodation, and recommended scope between architect, structural engineer, and cladding engineer. So that's all from my side. So if you have anything specific to answer, probably we can take questions now.
Yeah, thank you so much, Naveen. It was indeed a great presentation. Thank you so much for giving that insight. And we have received a lot of questions, which shows that this is such an important and popular topic for the people. So we'll take up a few questions out of that. And in case if we are not able to take any questions from the audience, so we will definitely reach out to you on mail and we'll respond to all the questions. So the first question which we have received is from Mr. Wasim Firoz, is about how to fix the settlement issue, which you showed in your presentation about the issue of settlement, how to fix that. Naveen, can you hear me? Naveen, Mir, can you check if am I audible to Naveen? Naveen, can you hear me? So Mihir, I discussed with Naveen. He had some technical issues, so he got disconnected. He's connecting again. So if you can give him that host, right, so that we'll be taking up the questions.
Sure, I will.
In the meanwhile, when Naveen is joining back, I'll taking up the questions, and he can add back on that. So the first question which Mr. Wasim has asked is how to fix the settlement issue. So to be very frank, fixing the settlement issue at the time when we are doing the facade designing is a challenging issue. It has to be fixed when we are at the civil work site designing, and it has to be settled there, and we have to ensure that all the three things in the settlement which was explained, like the uniform, the tipping, and the differential settlement about the crack, all these are the civil challenges. So it has to be taken care of during that time. So Naveen, are you back? So second question is Amaya, is what is the relationship between increase in the wind load and structural bite?
So, Salesh, I got disconnected.
Yes.
I'm back here. Can you hear me now?
Yes, Naveen, I can hear you. So, were you able
Sorry, I got this. So, what is the relationship between wind load and structural bite? Right, that's the question. So, in case of lap joint, silicon is responsible for holding the glass to the facade. So, essentially, your silicon is bonded to the facade. So as the wind load increases, so the suction generally the suction forces of wind load are much higher than the pushing forces. So as the wind load increases, the suction forces increases on the glass facade, and which asks for increased strength in the sealant to hold the glass onto the facade, and that is the reason you need to increase the bite. So as higher the wind load, higher the bite thickness. That is the relation.
Okay. One more question from Amaya is, rather than water test, can we go with any other alternative test to verify the water leakage or assurance of primary sealant?
So smoke tests have been very popular to understand the leakage point. It is more effective than the water test. We immediately can detect the discontinuity of the sealant. So smoke tests are another way of doing it. But generally, since hose test becomes popular because one of the cheapest way of doing it, but I think the more effective way of doing is to do the smoke test.
Yeah, thanks, Naveen. One more question is from Mr. Chetan is, for facade design, which method is considered? Limit state method or working stress method? What does the code says about it?
So it is purely a choice. So you can use limit state method, you can use working stress method. Popularly in India, we are still using working stress method to assess the to do the facade design, but we can essentially use the limit state method also. Why limit state is not popular? Because there is very small gap between the yield stress and the ultimate stress for aluminum, and that is the reason in most of the cases people actually do not look at limit state of design during for aluminum. For steel, this can be a area where a lot of saving can be done. But nothing wrong. You can use limit state or you can use working stress method, but you need to be worried about the fact that you should not mix doing the both. So you can actually mix also, but the one area should be done with one strategy. If you are using working stress method, use working stress method, or vice versa.
Okay. So next question is from Prachi. Is nowadays we all are experiencing frequent changes in weather. In view of the same, what will be the role by a facade designer?
So, facade designer role is increasing year over year. So as we are seeing the type of building which is coming up, or the type of innovation which is happening in facade design, there's a lot of scope facade designer can contribute to. But as far as the specifically related to the change in climate is concerned, I think temperature, the environment load, which is wind load and temperature load, that is the one thing which needs to be addressed from the perspective of facade designer. But if we talk about the entire scope, I think this session will not be sufficient to answer your question.
Okay. So regarding this wind load, one more question which is coming is from Ruchita. What is wind tunnel and how to design facade to take care of wind load arising due to it?
So wind tunnel is a method of, see, like I said in one of the slide, wind load is a probabilistic theory. So you based on the probability, you decide what is the wind load is going to occur on this building, applicable on this building. So wind load is a method where you actually do the simulation. So you make a kind of tunnel. actually you try to make a model of 500 meter radius, whatever falls in that 500 meter radius of that building, and then you try to model it. You make it in a tunnel and then blow a kind of wind, and you have various sensor which assess the pressure points at various locations, and then you arrive at what should be the actual wind. Like your Indian standard 875 does not help you with the complex structure. In those cases, you'll have to do a wind tunnel study to understand what are the applicable wind loads. And specifically in case of tall towers, you need to go with the wind tunnel testing. So since it is done in a tunnel, it is called wind tunnel test.
Okay. So one question which is coming on the movement of the building. What is the expansion contraction clearance which has to be given at Mullions and transom connection? It is asked by Mr. Rajesh Ramaswamy.
Yeah. So if you see that primarily depends on what is the movement to be accommodated. If we talk about the stick curtain wall, two stick curtain wall are popular. One is 50 millimeter, which has a sight line of 50 millimeter, and another is 60 millimeter, which has a sight line of 60 millimeter. So by default, a 50 millimeter curtain wall will have a edge clearance of 4 to 5 millimeter, depends on one design to another. And for 60 millimeter, it may be 8 to 9 millimeter. So 4 to 5 millimeter edge clearance means you may be able to accommodate 3 millimeter of movement theoretically. You'll also have to understand what is the kind of fabrication happening at the back end and what are the tolerances out there. If the tolerances in fabrication is 2 millimeters, then you are remaining only with 1 millimeter to accommodate movement. So you need to think it holistically. So generally 4 millimeters is 5 millimeters standard edge clearance. Most of the cases this is okay. In mid-rise, high-rise you'll have to simulate it case-to-case basis.
Okay. One very interesting question, Naveen. I'll take two more questions, I think, because of the time paucity. It is asked by Mr. Vinit. So moment displacement in a straight vertical facade is fine. How does facade behave for curvilinear or the bend glasses?
So very good question, I must say. So when you have any irregular structure, so like I said earlier, yeah, our Indian standard does not help us with complex structure. So all the thing has to be done with your finite element analysis. If we are not able to estimate the potential movement which this structure is going to make, we'll have to assess this using finite element analysis. We'll have to check what is the kind of structure it has, what are the kind of forces it can be acted upon, and then decide what is the kind of movement needs to be accommodated. So not easy to answer your question here, but in the curvilinear facade, you may have to go with a specialist advice. One thumb rule may not be sufficient here.
So we'll take up the last question, Naveen, for the day. It's from Mr. Ranjan. What are the considerations for lower and terracotta cladding interface?
Sorry, can you repeat, please?
Yeah, what are the considerations for louvers basically, louvers and cladding? Yeah.
Louvers and terracotta. So principles remain same. You need to understand what is the say if the material changes, what is the kind of movement this material may have. Like terracotta cladding has very low CTE. So as a component, this is actually a preferred component. Louvers, if it is made of aluminum, you need to understand where it is used, whether the ends are restricted or not restricted, or whether you need to design a component to take care of those stresses, or you want to accommodate those movements. So principles remain same, whether it is louvers or terracotta cladding or stone cladding or the glass facade.
Okay. So I think we have got lot many more questions, Naveen, but because of the paucity of time, we will not be able to take up all these questions here. However, we ensure that all the questions will be answered over email, and you can reach out to us as well as on the email ID which is given on this slide, which is seymour@aisglass.com. So in case if you have further doubt on this subject or any other subject related to glass, glazing, fabrication, facade engineering, or all the topics which we have touched upon in these 4 sessions, so you can write back to us. We will be happy to answer all the questions. So once again, thank you so much, all of you, to take out the time and attending this session. So that's all for the day. Thanks for joining. Thanks, everyone.
Thank you, everybody. Thank you.